Thank you for inviting me to this wonderful event. It's such an honor for me to be here. I'm a fire structural engineer from Italy, and SAFIR is the computational tool my team and I have been using to perform analysis, numeric analysis on fire resistance. Today, I will present to you some results on the steel automated warehouses. The results comes from multiple projects rather than a single one in order to highlight their specific characteristics. So before diving into this specific topic, I'd like to give a brief introduction to how fire resistance is assessed in Italy. In recent years, Italian fire safety rules are shifting from a prescriptive approach to a performance-based one. So under the prescriptive approach, structural fire resistance was typically defined by a single fixed value. As you can see here, there is just a number that we have to check. When we moved in a performance-based system, designers can now select among 5 different performance levels, depending on the characteristics of the facilities under consideration. So for example, level 1 focuses on the collapse mechanism. It is important to assess how the structure collapses and not when. This level is usually applied to buildings without occupants, like automated vertical warehouses, like the ones I'm going to talk in a while. Level 2 adds a very first safety check. The structure must remain stable long enough for evacuation and for emergency services to intervene, which is typical for industrial buildings. Level 3 requires the structure to remain standing for the entire duration of the fire. This level is typically applied to civil buildings like the one that you can see in the screen now. And this is a structure located in Genova, in the north of Italy, built in 1939. And we were asked to assess its fire resistance. Or it could be applied to a sports hall that we saw even earlier, where analysis must take into account for scenarios such as concert event and the possibility of a fire, for example, coming from the stage. Level 4 and 5 are the most demanding, as the building must stay standing and suffer only limited damage to ensure business continuity. This applies to hospitals, fire stations, and similar facilities. So we, as designers, perform our modeling using SAFIR to verify all these levels. We will focus now on level 1 with specific attention to automated vertical warehouses. But the first question is what is an automated vertical warehouse? These facilities are self-supporting structures in which the main structural frame and the storage racks are integrated. So here, for example, you can see a typical longitudinal section and the plane view, which shows, for example, the main structural component, such as the lateral bracing towers and the stacker crane aisle. This figure also highlights how the combustible materials are located in this warehouse volume. The main challenge with fire resistance when we are talking about automated warehouses is that they store huge amounts of combustible materials, resulting in a very high fire loads. At the same time, they are built with very slender structural elements, all classified as class 4, as the Eurocode will say, which makes them prone to local instabilities. It is pretty clear that the best way to understand how these structures behave in fire is through fire safety engineer. The methodology that we all know identifies three main phases plus a phase zero, we call it in this way, which involves gathering all the information about the structure. With phase one, we can define the thermal action that we can use in phase two to identify the temperature in the element, which can be used in the phase three to finally obtain the answer on the load-bearing capacity of the structure under study. So let's focus on each phase. So for phase one, for example, we use FDS to model the warehouse as fully loaded with pallets. We are aware, we all know that this won't be the case in reality, since empty spaces are needed for handling, but also for movement. But we decide to consider it as the worst case scenario. Each pallet is modeled as being composed of the stored material, wood and cardboard boxes, often wrapped in a sort of plastic film. Each pallet is treated as an abstraction with 6 sides, and in most of the case, each side is releasing an HRR of 500 kilowatt per square meters. This value is suggested by the Italian regulation and the Eurocode 1, and is suggested for materials characterized by fast or ultra-fast fire growth. Talking about the propagation, we consider it, and it is modeled using the lowest ignition temperature among the materials. Regarding the fire scenario, in our experience, we consider different possibilities, but we believe that those with ignition at the base and near the lateral areas are the most critical for triggering an implosive collapse. From different projects, we have seen that in the first 5 to 10 minutes, the fire remains very localized. Some areas reach over 1000 degrees, as you can see, while others stay near ambient temperature. Because of the high temperatures and also because of the slenderness of the structural sections, collapse is expected within this time frame. This means that we are actually dealing with a localized fire scenario where the cooler zones act as a rigid support for the heated areas. This is an important point that doesn't have to be underestimated. Here, for example, you can see the temperature slices from FDS for different projects where you can see pretty clearly the localized fire. Everything below the black marks has a temperature lower than 100 degrees. So a key part of phase one is understanding and using the results from CFD models. These results, which later become input for phase two, as I said, usually may come from many temperature devices, often located where the structural elements are supposed to be. For example, in this one case, we place almost 16,000 thermocouples devices in a 76,000 cubic meters volume, which will generate a large and complex data set to manage. So what do we do after? Basically, as a designer, we choose to divide the warehouse into zones. So the same curve coming from the devices we placed can be assigned to all the elements in the zone that we are considering. With this procedure, with this methodology, then the natural fire curves are assigned manually to many elements. So that could be easy to make an error, as we are human, so it is the probability are pretty high. On the other hand, the results from FDS can be transferred to SAFIR using the interface file. This file contains the radiation intensity calculated in different directions. So this approach allows SAFIR to create a more detailed and accurate temperature field in the structure because it automatically considers a spatial and temporal variation of the fire, geometry, and the orientation of the structural elements, shadowing effects, and configuration factors. So for this method to work correctly, the computational domains between FDS and SAFIR must match in a very good way, let's say that. So these analyses are highly demanding. They require careful setup, technical expertise, and please let me say a lot of patience for the designer because we really need a lot of passion to do it. Moving on, we have a look at phase 2. Basically, what we do is we do the thermal analysis. So these thermal analyses are performed using the thermal properties specified in the Eurocode. So if we consider the fire curve temperature as input, and we apply the curve to the frontier, for example, of the vertical column belonging to zone 1, we can see that the temperature, as we were expecting, seems to be pretty uniform. And that is because in this analysis, we are not considering where the fire and the elements are located. Plus, we don't consider any shadow effect nor the configuration factor. But when the data exchange file, when we use the interface file, when it's used, clear temperature differences appear. This is because SAFIR can calculate heat transfer from the fire to the structure, considering geometry, orientation, shadowing, and so on. So, for example, here we can have a look of how temperatures vary along the column of the first load level, showing the position of each element relative to the ignition fire. So, for example, we can see that on the left side, we can have the section from the braising towers, and we see that they have the ignition point on the right side, while the other one, this one below, has the ignition point, the fire coming from the left. And I think this is a very impressive results that we can get, especially because it shows us the distribution of the temperature in the volume. We can also, for example, assess the temperature differences of the most heated beams on different load levels. For instance, after 5 minutes, we can see that the highest temperature is reached by the beam on the 6th load level. Moving on phase 3, the structural model was then developed. So we know that we are dealing with a localized fire and very large volumes. So we are aware that a computational effort is pretty high. So what can we do in order to reduce this aspect? We decide to create a submodel. So for each scenario, for example, in this case study, we select the area where temperatures exceed 100 degrees, and we apply constraints where the structure is actually removed. So we define also appropriate releases between the individual members in order to take into account for the actual degree of connection between the various elements. Another important aspect, but at this point of the presentation, it should be pretty clear, is that all the elements are classified as class 4 according to the Eurocode. So this element can become locally unstable. So the best way would be probably to build a full structural model with plate elements to capture this behavior, but it's too complex and computationally very expensive. On the other hand, we have to take into account of this aspect. Otherwise, all the efforts we made so far, such as, for example, the determination of the thermal action, would be ineffective. So in SAFIR, there is a simplified method to reproduce this behavior and the effect of the class 4 ductility elements under fire. We consider a material called steel SL that has basically an asymmetric constitutive relationship, modify essentially only in the compression part in order to be able to take into account any local instabilities. So, for example, if we look at the section at the vertical columns, we are actually modeling the section as if it were made of 4 plates with different slenderness, and therefore 4 different materials. So while before we had like 25 sections and 4 types of materials, that only differed in strength. Now we have more than 200 sections and 22 different types of material, which differed not only in strength, but also in slenderness. So the model is getting a bit complicated. By performing nonlinear dynamic analysis, it is possible to observe the correspondence between the traveling fire and the progressive traveling failure of the structural element, which is really helping us. And with the new version of SAFIR and the new version of the post-processor Diamond, it is now possible to visualize also the displacement trend and also the velocity of the movement of the structure, which are drawn as arrows, which indicates the direction of the movements of our structure. We can also visualize the spreading temperature linked to the deformed shape of the structure. This is pretty impressive, in my opinion, because it shows us the way the temperature is moving in the volume. And here we can see just one transversal section to a better visualization. But we don't have to forget that our goal is to evaluate whether the collapse shows a tendency toward implosive collapse. So one of the best checks that we can actually do is plotting the vertical displacement of the beams mid-span nodes at different load levels, along with the horizontal displacement at the nodes located at the beam column joints at each load levels. So the figures highlights the pretty well-known, let's say, runaway trend for the vertical displacements, which progressively shift downwards. For the horizontal displacement, instead, we can see that some curves display a sort of change of direction near the end of the analysis, suggesting a potential inward collapse. So after the initial expansion, the displacement reverse, indicating that the columns tend to follow their horizontal elements as they collapse toward the center of the warehouse. This behavior represents to us a tendency toward the implosive collapse. By plotting also the axial forces of the beams, we can see that they first go into tension due to thermal expansion, then gradually shift to compression. So since expansion is restrained by columns, by the bracing towers, lateral bracing towers, compressive stresses build up. As stiffness decreases, the columns moves back, and the beams switch from compression to tension, activating the well-known catenary effect. So ideally beams fail first and pull the columns down. But we have to say it that this is the way supposed to be only if the connections hold. So for example, here we focus on level 3 and 4, for example, we can see clearly that in a fire, connection face extra stresses from restrained thermal expansion. And these extra stresses are not usually considered in the cold design. So, for example, a beam hinged to a column can develop the catenary action. So the connection must first resist tension and then compression and then back to tension again as the heated beam loses rigidity. So connections are usually assumed to have the same temperature as the attached structural members, which is pretty conservative since they heat more slowly due to the larger thermal mass and the shielding. Anyhow, we have to say that if a connection passes verification under this assumption, for us, designer, everything is safe. Otherwise, we need, and we did actually create a detailed thermal model of the joint in order to define local temperatures, which are often lower than the beam's average temperature. So in conclusion, I think it is important to mention that the computational time required for this analysis is pretty high. So leaving aside the FDS model, we are aware that running this simulation takes time, but we are considering all the section as class 4 section, and we are really able to model the propagation, the traveling fire using the FDS and SAFIR interface. So just to have an idea, to run like 3 fire scenario, it took us almost 1 month, 1 month and a half. But we know that it's pretty high, but we are confident that is the correct way, the correct approach. And these results are really showing us what is truly happening in such facilities. Finally, I would like to thank my colleague, Dr. Andrea Marino from the Italian firefighters for his constant support and his precious advices, as well the colleagues from Delta Fire, Marco, Mario, and Giulia, which helped me a lot in improving the FDS interface file. Finally, not least, I would like to thank you for your time, your attention, and I'm available now, or here is my email for questions or curiosity you may have. And thank you so much.